be on our way. Okay. Got the last two people came in, so. All right. Start the slideshow where we left off last time. But before we do, there it goes. Before we do, any questions from anything we've covered so far? Everything going all right? Okay. Where we're starting today is example 3. And, wow. Oh, here they are. So once upon a time, we had erasers in here, but they're up here on the desk. Be good when my work study gets started again. We signed the paperwork yesterday. These boards are in sad shape, and nobody else does that kind of stuff. So, all right. What do we mean by finding the zeros of a function? Make the function equal 0. Find the values for x, the input values, the parts of the domain that make that output 0. So, for A here, what would we do? A little louder? Okay, well, first set it equal to 0. Let me get my... Okay. Oh, there was one more announcement I wanted to make once we're recording now, and that's this. Normally today, on Thursdays, Tuesdays and Thursdays, I have office hours from 10:45 until 12:30, okay? Not today, I don't think, okay? I had to miss my trig class Tuesday because I had a doctor's appointment that went forever. So what I'm planning to do today is make up that class in the trig class with 2 classes. So we'll be 9:30 to 10:45 and then 10:45 to 12. That will make up the class we missed. So my office hours today are only 12 to 12:30. That's all, folks. So now, if no one in the trig class can stay, then we might move it to Tuesday. But right now, I would say that's probably what we're going to do. All right. Now, so what's the first thing we do? Set it equal to 0. 3x squared plus x minus 10 is equal to 0. And someone said factor. It sounds like a capital idea to me, but we got to see if it's factorable. Is it? I like to start with the first term. What's the only possible factorization for 3x squared? 3x times x. Okay? Where do we look next? The sign of the last term. That is a minus. What does that tell you about these 2 signs? They're what? They're different. One's plus and one minus. You have a preference? It may be trial and error. Want to just do plus minus? Let's see what happens. Now, you got several factorizations for 10. Which one you want to try? 5 and 2 in that order. Let's try it and see what happens. 5 and 2. Okay, how do we check to see if this is the right factorization? Don't just move on from here. You may have gotten it wrong, okay? You flaw it. 3x times x is 3x squared. 3x times a minus 2, negative 6x, plus 5x would be, second, what one is? Negative x. Close but no cigars, okay? That's a plus x. The coefficient's right, 1, but your sign's wrong. So what do we do here? Change the signs. You got the numbers right, change the sign, okay? So you may not have learned to factor this way. I'm probably the only person that does it this crazy way, but to me it works. Okay, let's check it again, make sure. 3x times x is 3x squared. 3x times 2 is 6x. Minus 5x is x. Minus 10, yes, it works. Now what? Set each factor equal to 0. 0 product principle. 3x minus 5 equals 0, or x plus 2 is equal to 0. What do we do with that first one? Add 5 to both sides, and that gives us 3x, this adds to 0, is equal to, not that hard, 5, okay? And then what? Divide both sides by 3. You're trying to isolate the x, so you have x equal 5/3. Is that legal? Can you have a 0 that's a fraction? Of course. You can have an irrational number. Positive, negative, doesn't matter, okay? Some real number value for x. That's one. How about the second one here? Subtract 2 from both sides, and you get x is equal to -2. There's our two suggested solutions. Now, we haven't hit this yet, but I'm going to tell you now. If you have a maximum exponent of 2, what's the most number of zeros you expect to have? 2. We found 2, don't look any further. Unless we missed them, okay? Now, sort of hesitate this, but you really should do it every time. It's not required, but I don't like to make mistakes. I make plenty, and I don't like it though, okay? So I want to make sure I've got it right. Let's plug in x equal 5/3 here. What's 5/3 squared? 25 over 9 multiplied by 3, and you get, okay, let's not do it that way. Let's divide the 3 into the 9 and get, it works the same way. It's just this is the lazy way, okay? You work too hard, okay? 25 over 3, right? Because the 3 cancels out one of the 3's in 9. So 25/3. You might want to write that down. 25/3. If you don't know, if you need to do 75/9 and then divide out the 3, do it that way, okay? Now, plus 5/3. And what's 25/3 plus 5/3? Say again? Okay, 30 over 3, is that what I heard? And what's 30 over 3? 10 minus 10 is 0. You know that one works. That was a hard one. Let's see if the easy one will be any better. Okay, what's -2 squared? 4 times 3 is 12 minus 2. 10 minus 10 is 0. Yes, that works too. Okay, so we know we got the right two answers. We got 2. That's all we could get, maximum, and both of them work, so don't look any further. Those are your 2 zeros. Okay? Now, how about that next one? Anything suspicious about it? Besides that rhyme is here. Okay, that's pretty suspicious. Okay. There he is. All right, what do we do? What do you notice about it? Ah, you got one of those radicals, a square root. What does that tell you? Okay, let's say that in math. 10 minus x squared, that's what's under the radical. How do we say it can't be negative without writing all those words? See, mathematicians are lazy. You use symbols. Make it short, sweet. It has to be greater than or equal to 0. Very good. Can't be negative, so that means it's greater than or equal to 0. What do we do now? How do you do that? Subtract 10 from both sides. That'll work. Minus 10 minus 10. Okay, those go away, and that gives you a -x squared is greater than or equal to 0. -10. I can't read. Okay, -10 there. Squeezed it in. All right. We may have, okay, what do we do next? What do we do next? Divide by -1. What does that give you? So it'll be x squared. Ah, very good. Less than or equal to 10. Anytime you multiply or divide by a negative number, which is what we did there, you flip the sign of the directional inequality. Remember to do that. Adding and subtracting positive, negative doesn't change signs at all. Multiplying or dividing positive doesn't change the sign at all. But multiplying or dividing by a negative number flips the direction of the directional inequality. Now, if that was not equal, it's still not equal, you know. But a directional inequality, you flip the direction. Okay, so x squared is less than or equal to 10. What do you do next? Take the square root of both sides. That is true, except you got to be a little bit careful here. Okay? What you have here, what x squared less than or equal to 10 means is x times x is less than or equal to 10. Now, what does that tell you about the two? Is that the way we want to approach this? Yeah, I think it is. Okay? Either you got a product of two entities, and that's less than or equal to 10. Okay? That means those entities have to be either, and 10 is a positive number, so either x has to be positive or negative, right? So if we were taking a square root, we would say that x is I find the best way to do this is do it on a number line, okay? Do it on a number line, okay? 0, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, something like that. Positive, negative. Where is, okay, if you take the square root of both sides, what do you get? X, and I'm going to leave this blank for a minute, the square root of 10, right? Yes, plus or minus the square root of 10. Now that's a little confusing to say less than or equal to plus or minus square root of 10. That gives you way too many options. But let's write it down, okay? Now, okay, let's take a look at that and see what it says, okay? What is approximately the square root of 10? Just give me a rough ballpark figure. Something greater than something and less than something. Between what two integers? Between 3 and 4, exactly. A fairly small number. 3.1, 3.2, I don't know. Let's just find 1, 2, 3 and a little bit, and negative 1, 2, 3 and a little bit. Here is minus the square root of 10, and here is plus the square root of 10. Okay? Now, to me, this is the easiest way to do this. What we want is the square of whatever number you pick out here has to be less than 10. So let's go to minus 4 here. Minus 4 squared, is that less than or equal to 10? Yep, negative 4 squared. That's what? That's greater than 10. So obviously, this part out here is not in the domain here, right? Because that's, okay. How about in between? Let's pick a real easy one in between plus or minus 10. 0, all right. Is 0 squared less than or equal to 10? Yes, it is. So I would contend to you that everything within these 2 points, everything in here is in that domain. Let's go outside the domain, outside that here. 4 again. What happens if you put 4 squared? That's outside too. So this is not in the domain. So all this is just to let you know what values of x qualify. We haven't even started working the problem. We just need to say, comma, negative root 10 is less than or equal to x is less than or equal to root 10. That's what all that was for, to let us know what is our implied domain. All right, with that in mind, let's solve the problem. What would you do there? We're finding the zeros. We're finding the zeros. What's our first step? Setting it equal to 0. The square root of 10 minus x squared is equal to 0. Okay? Now what? What's our goal here? Find out what 10 is. I mean, x is. We know what 10 is. Find out what x is. Well, x is buried in something here. What's the first thing you got to dig up or get out of the way before you can figure out what x is? The square root. How do you undo a square root? Square both sides. And what does that give you? 10 minus x squared. When you square a square root, you get that. And when you square 0, you get 0. Hey, that wasn't bad. Time out. Anytime you square both sides of an equation, it guarantees what we did here for fun, and because we want to make sure we were right, this was optional. You have to check all your results when you square both sides, because you may have, in that action, introduced what they call an extraneous root, a root that really isn't true, because you squared both sides of the equation. I think we'll be okay here, but you always have to check these answers. What do you get here? What do you do next? Okay, add x squared. I was hoping someone might say that. Add x squared to both sides. Is that what you're saying? Okay, and when you do that, what does that give you? Okay, 10, because these go away, is equal to x squared. And then what do you do? This is something we just were doing. Okay, set square root of both sides, and that would be x equal plus or minus the square root of 10. That's not a perfect square, so we leave it like that. So what? What's that? No, this is doing what the problem asked for. What we were doing before was determining the domain of that. Now, both of these answers here fall in our domain, just barely. They're the outside pieces, but they do fall in the domain. If one of our answers here was out here or over here, not an answer, okay? But both of these do fall into the domain, so you're fine, okay? Almost had to be. But we still need to check the answers. So let's do it. If we put positive square root of 10 in for x squared, what is square root of 10 squared? 10. 10 minus 10 is 0, square root of 0 is 0. Yes, that works. If you put a negative square root of 10 in for x and square it, what do you get? 10, because negative, you square a negative number, it becomes positive. Square a square root, it becomes what's under here. So again, you get 10 minus 10, 0. Yes, both of those work. They're in the domain. Those are your answers. Okay? Now, you could write it as x equals positive square root of 10, x equals negative square root of 10 if you want to write it twice, but you do have two answers. This is two answers because of that plus or minus. All right, the C one. What do you notice about it? Yeah, it's a fraction. Now, fractions aren't bad. We love our fractions, right? Yes, okay. But what do we have to watch for? Okay, denominator can't be 0, so the denominators we worry about. If that were just 5 here, we aren't going to worry at all because 5 is not ever equal to 0. It's 5, it's not 0. But when you have the variable in the denominator, that's where you worry. So what do we have to do? We have to say that. What'd you say? Okay, the denominator can't be 0. The denominator is t plus 5 cannot equal 0. Now solve that inequality. Subtract 5 from both sides, and that gives us t is not equal to negative 5. So that's the only restriction we have here. T cannot equal negative 5. Now we go on and do our problem. Okay? Do what they ask us to. And what do you do? Set that equals 0. Is that what you said? So 2t minus 3 over t plus 5 is equal to 0. That's your function equals 0. Finding the zeros. Now, there's a couple ways you can do this. Okay? And I'll talk you through both of them. How would you do it? Okay. That was one way I was thinking. We'll first mark Yolanda here, and then multiply both sides of the equation by t plus 5. Now, what is other thing you don't ever want to do? You can't divide by 0. What's something you don't ever want to do? Multiply by 0. Because that wipes out all the meaning of the problem. You know, whatever you have, you multiply it by 0, you get 0 equals 0. You lose all the meaning. Well, we already know this can't be 0 because we said that. Okay? So no, it's safe to do that. It's the only problem with multiplying both sides by something with a variable in it because you don't want to multiply by 0. But this one can't be -5. Get out of there. Okay. That's not you, I meant, okay. Multiply by t plus 5. All right, now what does that give us? The t plus 5's go away on the left, leaving us just 2t minus 3 equals 0, because 0 times anything is 0. Okay? So, now time out. Here was the other option. And this is usually how I think about it. If we have a fractional form here, a over b is equal to 0, what does that tell you? If you have a fractional form, something over something is equal to 0, what does that tell you? The numerator has to be 0. Okay? If you think of a numerator you can put over anything else in the world and give you 0. 1 over something isn't going to be 0. 17 over something, -3 over something, nothing over something will give you 0 unless that something is 0. Okay? It doesn't matter what that denominator is, except it can't be 0 itself. So we could have just jumped right to this thing. You have a fraction form here equals 0. That means that numerator has to be 0. You could have gone straight there without multiplying. So 2 ways to do it, but if you see that way best, go for it. Now what? Add 3 to both sides, and that gives us 2t is equal to 3, and t is equal to 3/2. Is that what you said? Okay, yeah, divide both sides by 2, and you get t is equal to 3/2. Okay. Now, probably ought to check this too and make sure it works. Well, the first thing you check, 3/2 is not equal to -5. Good. Okay. We couldn't have an answer that was not in your domain. That was in the domain, so we're okay with it. Okay? Boy, this looks like fun, doesn't it? Okay. Right here, this form here. 2 times 3/2 is 3 minus 3 is 0. Yes, that works. We don't have to worry about the denominator. It's not going to enter the picture here. So there's the one and only answer, and we know it works. Okay? You could have done 3/2 plus 5 would be, what's that, 13/2, but 0 divided by 13/2. It's still 0, so why waste your time? I mean, spend your time. Okay. Any questions on any of those? That was our solution there. All right. Now, again, when you have fractions and denominators and stuff, you can't count on the same rules you did with polynomials. But it's funny, isn't it? That x was squared, you had 2 solutions here. That t was only to the first power. Sure enough, the only one that was 1 solution there. You can't always bank on that when you have these other forms. That rule only works with polynomials, but man, it seems like it carries through at least some of the time on the others. All right. That's neither here nor there. We don't know where it is, but it is. Okay, let's go. All right, let's do that first. First thing they do, set the function equals 0. That's what it means to find the zeros of a function. Okay? And when you do that, they then say factor next. And sure enough, they did it without too much struggle because they knew the answer already. And then you set each of those equal to 0. And the 3x minus 5 equals 0 produced x equal 5/3. We got that. And the x plus 2 equals 0 gave us x equal -2. Now, I don't think they showed how you check it, but you can check it. Good idea to check it. Okay? Let's go to the B. Oh, they drew a picture of it, which is a good thing to do too. Okay? And if you draw the picture, and later we'll see that we could tell already this is going to be what shape? A parabola. Any quadratic function is going to give you a parabola. I want to say that. Well, I also think never say never. Okay, never say always. You know, that's generally the thing. Okay. Now, positive coefficient means means that parabola is opening up, so it holds water. Okay, so that's another thing. We haven't gotten there yet, but we're going to get there. And we can fiddle with the other parts of it here if you wanted to. But let's look at, if you have a graphing calculator, you'll see that sure enough looks like it's passing right through -2, 0. And that's x equals -2. That's where your y or your f of x is equal to 0. Sure enough. X equals 5/3. I know it's between 1 and 2, but I can't say square 2. I know that's 5/3. Okay, it's just something maybe even greater than a half. But it's sort of hard to pick out exactly what it is. 1 2/3 or 5/3. Sure, it looks right. Okay. Now, one other thing you could have done very easily if you're graphing, and we'll get to this later, is these are called your x-intercepts because that's the place where the function intercepts the x-axis. There's another intercept. What's that? Y. What's true about a y-intercept? Okay. Obviously, it has to cross the y-axis. But what's true about every point on the y-axis? What? Okay, it can only touch once. If it touches, it's only going to do it once, right? But what's true about every point on the y-axis? Give me the coordinates of that point. 0, -2. How about this one? Ah, the x is always 0. Okay, so that's what you can do here. Set x equals 0 here and here. And what do you get? Alpha of x, which is? Yes. No, f of x is, if you say x equals 0, f of 0, f of x is, what is it about functions? F of x is always y. Your y is -10. Look at that. The y crossed at -10. The y-intercept is 0, -10. Easy point to pick out of most functions. Okay? Set x equals 0, you get your y-intercept. And what we just did, set y equals 0, and your x-intercept. Okay? Easy to pick out some points. And frankly, the y-intercept is the easiest. Okay, good. The graph showed it to you. You could have plugged in the values. That works too. Now, how about that one? What do we say the first thing to do? They ignored the fact that you got a radical there. They just went right to the problem and squared both sides. And that gave you 10 minus x squared is equal to 0. And then they did the same thing that Amber, is that right? No, yeah, did. She added x squared to both sides, and then take the square root of both sides, and that gave you plus or minus the square root of 10. Now, they didn't check it and make sure that was in the domain. We did. It was, so we're fine. And then they show this. The zeros are x equals minus 10, 0, minus square root of 10, 0. And see, that's between 3 and 4. 3 is halfway between 2, -2 and 4. Yeah. So, yeah, that looks about right. And I don't know if you realize this, but that forms half of the circle. You weren't expected to know that, but let's go back to our original problem. This is beyond the scope of the course, okay? What was g of x? Just like f of x. What is it? What is f of x always? Y. Why not? Okay. So that would be y is equal to the square root of 10 minus x squared, right? And then we square both sides, and what does that give us? Y squared is equal to 10 minus x squared. And then move the x squared over, you get x squared plus y squared is equal to 10. Does that look familiar to any of you? We haven't hit it in this course, but you may have hit it before somewhere in your past life, okay? What that is the formula for the equation of a circle, okay? These two coefficients are the same. They're both squared, and this is the radius squared. X squared plus y squared is equal to r squared. That's it. And the radius would be, this is the radius squared, so the radius is plus or minus, is square root of 10. The radius is only positive. So that would be a whole circle. Well, why didn't they draw the whole circle here? Or was that your answer? This is a function. Would that circle be a function? No, because the vertical line test we cut it twice. So therefore, we only do half of it. Okay? Now, if the original problem had been minus the square root of that, it would be the bottom half of that function, of that circle. Okay, so that's the semicircle. That's beyond the scope of what we've done so far, but nice to know anyway. And of course, we could find the y intercept. How do you do that? Plug in 0 for x, and what does that give you? Again? Square root of 10, and there it is. This is minus square root of 10, that's plus square root of 10. That's square root of 10, just past 3, not quite 4. So yeah, square root of 10 is your y-intercept. So that would be 0 square root of 10. And notice it's positive, that means it's the upper half of that circle. All right. That was way more than what you paid for, but no extra charge, okay? All right. Any questions on that? Okay, let's look at that third one. We set that function equal to 0. They don't worry about the fact whether it's saying, okay, now you were already here or did you just come in? Yeah, I thought you were, okay. Confusing me here, okay. And then, what did they say to do? They multiplied both sides by t plus 5, just like Amber did. But you could have also just said, that means the numerator has to be 0. Either way would have given you that result. Solve that, and you get t equal 2t. Oh, they do all the steps there. 2t is equal to 3, and t is equal to 3 halves. Okay? And guess what? I bet you they're going to graph it, aren't they? Let's see if they do. They just graph part of it. Okay? We'll get to how you do the whole thing later. Okay? I don't know. I'll go and show you how to do it now. They almost showed you how to do it. But sure enough, this point here does cross the x-axis. But that's not the whole picture. That's not the entire graph. Okay. What was the first thing we said about this? T cannot equal negative 5. So if you had gone on over here a little bit further with your x-axis, it would be 1, 2, 3, 4, 5. Negative 5 would be here. What you can do there is everywhere along that line, didn't take. Oh, there it goes. Okay. Everywhere along this line, t is negative 5. Well, guess what? It can't be negative 5. So therefore, that line is forbidden. You cannot cross it. And that's why this function here appears to be heading downhill fast. Okay? But it never crosses that line. What we call that, how would you describe that line? Yes, it's a vertical line, and we call it a vertical asymptote, meaning it doesn't touch it. Can't touch it, can't cross it. Okay. Now, there's something else that we haven't done yet, we'll do later. I'm going to give you a hint, heads up on it. Here's what it is. Look at the ratio of the leading terms here. The ratio of the leading terms for this is radical expressions, rational expressions. What's the ratio of those leading terms? 2 to 1. So, and this is a y here, so y equal 2. There's y equal 2. Well, then you could draw, I'll go on and put it red too, if I can get it to change. All right. At y equal 2, we will put that. That is called a horizontal asymptote. Now, there's a little bit of a difference between a horizontal and vertical asymptote. Horizontal asymptote, it can touch it or cross it. But what it's doing, that's where it goes in the long run. This one isn't going to do it. It's going to keep on trucking. Okay? And so going back to a dark color, it just keeps on going out here, but never reaches y equal 2. Does anything look a little unbalanced here? there's nothing over here. The only value that's not in your domain is -5. We've accounted for that. What about these values over here? Okay? Two choices. They're either in this quadrant or they're in that quadrant. Okay? So if you really wanted to see, pick another value like out here, like maybe -6. Plug that in here and see what you get. 2 times -6 is -12 minus 3 is -15. -6 plus 5 is -1. That would be +15. Is that what you said? +15. So that would be somewhere up here. That's 2, 4, 6, 8, 10, 12, 14, 16. Somewhere here at -6 you would be there. So guess what? Here's the other part of the picture. Okay, mine's not very pretty, but you get the idea. Don't worry about this. That's beyond what we're doing now. But I just wanted to let you know they didn't draw the whole graph. They just drew the part that had the y-intercept. But there were other pieces to it out here. You can forget about that now if you want to. You hadn't remembered anyway, had you? Never mind. We won't go there. Any questions on that? Okay. Oh, let's hope so. Okay. You will have graphing on just about every quiz and every test. This book loves graphing, and the questions come out of this book's test bank. But usually it's only be 1 or 2, to graph. I'm not going to ask you to graph something we haven't covered in class. So if you had just done that, that's all the book did, that's all you'd be responsible for. Or fun.
No.
Oh.
On a graph, no.
Yeah, okay. Yeah. It's.
Are we allowed to bring our graph and calculator?
Absolutely. Okay. Yeah. We want you to use all the tools you have. Guess what? In real life, your boss isn't going to say, but you can't use a calculator. I want you to figure all this stuff out. No, he wants, I want the right answer. I don't care how you get it. Now, I do care how you get it, but, yeah, let's be reasonable. You can have graphing calculators. Okay. In fact, some problems are almost set up for them. Okay. Now, guess what? There's a checkpoint at the bottom of the page. But as soon as you get out of class and have time, try to do that checkpoint. If you can't get it, if you can't remember how we did it, go to LarsonFreeCalculus.com. All right. Next thing is increasing and decreasing functions. That doesn't sound too bad. Hopefully it's not. Here's what we got. The more you know about the graph of a function, the more you know about the function itself. Let's consider the graph shown here. Weird little function here. I would contend this is a piecewise defined function. It's defined with one function value here, another one here, and another one there. Piecewise defined function. You can always pick those out. Okay? Now, as you move, and here's the key, from left to right, from low numbers to higher numbers, that could be large negative numbers and not as large as negative numbers, left to right. What is this function doing from, what's the domain of that function? Yes, all values between -2 and 4, including the endpoints because those are solid dots, right? What's the range of the function? Between 1 and 4, counting 1 and counting 4. Very good. So let's start at the farthest left of that domain, which is -2. As you go to the right from -2, what's that function doing? Going downhill, decreasing. Okay? Until it gets to where? The function gets to 1, but your x, this is x, the x gets to 0. You always refer to the limits of the function, the values of the function is the x value, the independent variables. Yeah, the function value goes from 4 to 1, but the independent variable goes from -2 to 0. That's where the function's decreasing. Then what happens? It's a constant function from 0 to 2. Yes, you choose that to be the x value. Because if you say it's a constant value from 1 to 1, of course it is. If it's constant at 1, it's 1. You give the x value, constant from 0 to 2. And then what? Increasing from 2 to 4. You got it. Okay. they usually do it in interval notation. Don't worry about whether you square the brackets or parentheses. It doesn't matter on the increasing, decreasing. Okay? Usually they just put them in parentheses. -2 to 0, 1 to 0 to 2, 2 to 4. Just put everything in parentheses. Even though you know the endpoints are counted, if you put brackets, it's fine, but you don't have to worry about that. Okay? So, here's how we say it mathematically. And that was easy to see. The verbiage here might seem a little more daunting, but it's not bad. Okay? A function f is increasing on an interval that counts some period there, like -2 to 0, stuff like that. Is increasing on an interval when for any x1 and x2 that are in that interval, okay, as long as x1 is less than x2, so x1 here, x2 there, inside the interval. For any x1 and x2 in the interval, and x1 is less than x2, not less than or equal to, less than x2. That implies, since the function's increasing, if the input is smaller, the function's going to be smaller. If the input is larger, the function will be larger. If it's an increasing function, that implies f of x1 is less than f of x2. And on the other hand, depending on how many hands you have, a function f is decreasing on an interval for any x1 and x2 in the interval, as long as x1 is less than x2. If it's a decreasing function, that means the f of x1 has to be greater than the f of x2. As you go left to right, x1 to x2, because that's less, then the function values are going downhill. So f of x1 is greater than f of x2. So it's saying the same thing, it just has some weird notation. Now, a function is constant on an interval when for any x1 and x2 on that interval, and it doesn't matter the order now, f of x1 is equal to x2. For everyone in there, that means it's a constant function. If those are always equal in that interval, that's a constant function. Make sense? Good deal. All right. You tell me, what is that first function doing? Okay, it's increasing over the entire interval. And since we don't have an endpoint listed here, they don't put a dot there, we assume this is from negative infinity to positive infinity. Of course, we have to go way downstairs and upstairs, everywhere. Now, don't fret this. Okay, here's your function. It's called the cubic function. Okay, and does it look like it might be constant in there somewhere? Yeah. It looks like it might be, but if you check any points, that would be some point close to 0. Pick a point close to 0. 1, you would see 1's right here. Yeah, we know there are no constants there. Pick something really close to 0. 0.01. Okay? So, what is it at 0? 0. 0.01. If you cube 0.01, anyone know what you would get? Yes, you have 6 zeros and a 1. Well, no, actually 5 zeros and a 1. Total of 6 places. 0.01 cubed. If you do it in your calculator, that would be 0.000001. Total of 6 decimal places. That's pretty close to 0, but it's still greater than 0, right? And if you put a negative in here, and cube it, that would come out negative, so you'd be a little bit less. So you're not far off, but it's not constant. It is, this is less than that, yeah. Okay, so yeah, that's increasing everywhere. Okay, how about that B1? How would you describe the behavior there? Oh, let's actually write that down. Use the graphs to describe increasing, decreasing behavior. So this is increasing from minus infinity to infinity. Okay? The B1, what would you say? Increasing from negative infinity to -1, excellent. And from, it's decreasing from -1 to 1, increasing again from 1 to infinity. All right, that's how you put it. You see, you're always putting in here your domain pieces, okay? And see, we don't have to put a bracket or anything else, just give the interval, okay? Negative infinity to negative 1, it's increasing, and it's increasing again from 1 to positive infinity. It's decreasing between negative 1, x equals negative 1 to x equals 1. See how you write that? Okay. You tell me what to write on this one. Increasing, negative infinity to 0, very good. Constant, from 0 to 2, very good. Decreasing from 2 to infinity. Okay. Now, this, by the way, was a piecewise defined function, and it happened to have those same limits. But don't be confused by that. You could have had a piecewise function that was a parabola that was increasing and decreasing, and then it changes. So you don't always have the same endpoints here. They may not. Don't do that. You look at the function and see what's happening. Sure enough, you got it. Let's see how they did. Any questions on that before I go to it? Anyone still writing? Okay. You got it? Okay. The first one, the function was increasing over the entire real line. They don't give an interval. The second one, the function was increasing on the interval from negative infinity to negative 1, decreasing from negative 1 to 1, increasing again from 1 to infinity. Just like y'all said, okay? And the C one said the function is increasing from negative infinity to 0, constant from 0 to 2, and decreasing from 2 to infinity. And notice on this, they always just put the intervals in parentheses. Don't worry about the endpoints. If you put the brackets, I don't care, you can. Now when you're doing a piecewise defined function, like they did back here, here you would need brackets. This would be negative infinity to 0 parentheses. This would be 0, comma 2, bracket, 0, comma 2, bracket. And this would be parentheses 2, comma infinity, parentheses. When you're defining a piecewise defined function or something like that, yes, you define that whether you count the endpoints or not. But when you're talking about intervals of increasing, decreasing, and constant, just put the interval, which is, you don't worry about the endpoints. Okay? But if you put them, it's not wrong. Okay. Yes? Okay, because you're looking at, okay, good question, excellent question. Okay. You're talking about this one here? Yeah, okay. What you're referring to in your interval is, you're saying it's decreasing. You said that. Decreasing, meaning it's going down, and the interval from 2 forever, that keeps going down. This is the basement, it keeps going down. It never goes, I mean, the way it's drawn here looks like it's a straight line going down. So yes, it's going down, but the interval is from x equals 2 to x equals positive infinity. You're referring to the, I'm sorry, t's. Okay. Referring to the t's, not the y's. Okay? In the interval. Yeah, that's what you do. The pieces of the domain. Excellent question. Excellent question. Okay, if you ever have something that's a fuzzy, ask it. Yeah. I was in the Navy, and Navy schools aren't reputed to be all that great, but in every school I ever went to in the Navy, the instructor always said that they must have trained them to say this. They say, there's no such thing as a dumb question except the one you don't ask, okay? If you have a question and ask it, it's not dumb. If you have a question and don't ask it, that's dumb, okay? All right. So I'm not going to bother myself on naval, but that is not bad. Okay. So to help you decide whether a function is increasing or decreasing or constant on an interval, you can evaluate the function for several values of x. Use some test values in the interval, see what's happening. However, you'll need calculus to determine for certain all the intervals for its functions, increasing, decreasing, and constant. We're not there yet, but that's the carrot out there. Yeah, take calculus. You can find this out. Yes. All right. Hopefully you will. All right. Let's see. Now let's talk about the points at which a function changes from increasing to either decreasing or increasing to constant, which changes its increasing, decreasing, or constant behavior are helpful in determining the relative minimum, relative maximum values of the function. Okay? They won't tell you for sure. Yeah, they will. Yeah, they will help you anyway. Let's put it that way. So here's the definition. These are words here, but you can figure them out. A function value, f of a. Okay, now that's the value of the function at x equal a, t equal a, at x equal a. The function's value is f of a, whatever that is. That is a relative minimum of f when there exists on some interval x1 to x2 that contain a. A is somewhere in between x1 and x2. x1 less than x, and x is less than x2, and a is somewhere in between there. Okay? On that interval, some interval, x1 less than a, x2 greater than a, some interval there, for every x1 less than x, less than x2 in that interval, that implies that f of a, if that's the minimum, is going to be less than all the other f of x, less than or equal to. Than all, okay? So what that means is, if your function is like this is the minimum if all the rest of the values are greater than that value. In other words, this value is less than all this. And of course, that would be a relative maximum if that f of a, relative maximum of f, when on that same interval, x1 to x2, a is in between there, contains a such that all the x1s less than x less than x2 in that interval, every one of them, f of a is always greater than or equal to all those other x values. Okay? Alpha vectors. Okay? In other words, the functions are always, if it's relative minimum, that's the lowest it is on that interval. If it's relative maximum, it's the greatest it is. Let's go back a picture or two. Okay? Does this have a relative minimum or maximum? Second? Okay. Okay, that would have, but you see, infinity is not a number. It has to be a number. Okay. So no, this is increasing everywhere. Everywhere. No matter how low you get, that's not a minimum because you can go further to the left and it's going to be even less. How about this one? This one? A relative maximum right there. See, all around that, everything is less. That's the maximum. That's the mountaintop. That's the peak. And this one? Relative minimum. That's the valley. As low as you can go in that interval there. Now, is this as low as you can go, period? No. Over here, it keeps on going down. But this is a relative minimum. For all the values close to that, that's the least value. Same thing here. This one gets higher, but for all the values around that, -1, all the other values are less than that. So that's the relative max, relative min. Now this next one is just bizarre. Okay. Everything up here is a relative maximum. All the points here. Because everything else is either less than or equal to that. Less than on this side, equal on this side. Equal on both sides. Equal on this side, less than that side. So that, this whole line here would be a relative maximum. Every point on there would be a relative maximum. That's bizarre. Usually we stick with curves that have definite turning points. Okay. Say again? Was there a question? Okay. Okay. So, here's another one. And they give you all the answers. Boo hiss. Okay. This is a relative minimum because all the values around there, the f values, the values y here, are greater than or equal to the value here. Now you can't get too far away, okay? Actually here you can. That's actually an absolute minimum. No. It looks like this function comes down and keeps going down. So it looks like if that does continue, that would still be relative minimum. Okay? That one? Relative maximum because around that, all the other F values, the Y values are less than or equal to that. Not an absolute because that is higher. And it looks like this one might be higher too. Okay? Another relative minimum, not absolute minimum, but that anywhere around that, all the other values are greater than or equal to that. But obviously not an absolute minimum because that. Now notice the singular is minimum and maximum. The plural is minima and maxima. That means it came from Greek, I believe it is, right? Like alumnus and alumni and alumni and whatever. Okay. So here's another relative maximum because around that, that's the times you can. Okay. Make sense? Okay. So usually if you find the endpoint of an interval where it's increasing or decreasing, the endpoint usually is going to be a relative or maximum. Okay? If this has an endpoint, not an infinity, but an endpoint of a decreasing function, that's probably going to be a relative maximum. That's going to be a relative minimum. Increasing, probably this endpoint is going to be a relative minimum. That one's a relative maximum. Unless it's an infinity, then it doesn't have one. Okay. Any questions on that? Okay. All right. Trying to find, yeah, okay. When we get to the next chapter, you'll study a technique for finding the exact point of a second degree polynomial. What do we usually call a second degree polynomial function? That's a special name. Quadratic function. A second degree polynomial function or a quadratic function has either a relative maximum or relative minimum. And it only has one because what's the shape? A parabola. And parabola either has one minimum or one maximum. That's all. And we can figure those out. The rest of them, you almost need calculus. Okay, for the time being, however, you can use your graphing calculators, okay, or graphing utility to find reasonable approximations of those points, okay? Now, if you don't have a graphing calculator, just try a few points, like it said before, see if the function is increasing, decreasing, and when you find it changes, pick some point in between there, and that's going to be close, okay? It takes a little more. Those graphing calculators will save you some time, but they cost some bucks, so you decide. Example 6.5 here, they don't have a they don't have a on the slide, so let's just do it here. Use a graphing utility, if you have it, to approximate the relative minimum of this function. F of x is equal to 3x squared minus 4x minus 2. Okay? Now, and what they say here, to find the relative minimum. So they've already told you it's going to be a relative minimum. Thank you very much. Other problems will just give you a big, long, hairy polynomial and say, find all its relative max or min. They told you this is going to be a minimum. So how would you begin? You can use a graphing calculator. I see you draw it out. But we can do it without one. What's a real easy value to evaluate that at? 0. Yes. What's alpha of 0? Tell me. Alpha of 0. -2. Excellent. Okay? Now, you can choose to go either to the left or to the right. I find it a little easier to go to right. I like positive numbers a little bit better than negative numbers. So let's pick one to the right of that. Alpha of 1. Let's do 1. Okay? What would that be? Now, this one's pretty easy too, because 1 squared is 1 and 1 is what? X is 1. So you just add the coefficients. What does that become? Do it however you like to. Say again? -3. So we're still getting less. Okay? So therefore, I'm going to keep going to the right because we're looking for the relative minimum. So what would be another one you might choose? F of 2. Why not? That one's going to be a little more work, but not too bad. That's going to be 3 times 2 squared minus 4 times 2 minus 2. Everybody knows how to do that, right? I'm doing too much talking now. We're running out of time. What does this become? 3 times 4 minus 8 minus 2. That would be 12 minus 10 equal 2. Hey, we suddenly turned up. So guess what I know? I know the relative minimum is somewhere in between. It's either in between these two or in between those two. Okay? Would you agree with that? Okay. Now, which would you guess? Since that went up so fast, I'm going to guess the relative minimum is between those two. It came down, and I don't know. But you see, negative 3 to 2, it just seems like it's on the way up there. It has to be. So I'm going to guess something else. So let's pick a point in between those two. Alpha of 0.5. And you know, you can do this on a calculator, can't you? You can do 3 times 0.5 squared minus 4 times 0.5 minus 2. I picked it, okay? I picked a number between 0 and 1. I'm guessing my relative minimum is between those two. I don't think it's between those two because that seems to be on the way up. I'm guessing between these two. I know it's not between those two. Well, no, we didn't have another one. But this is on its way down, and then it's way, way up. So I'm guessing it's somewhere between that. What does that give you? Anyone do that? Not hard on a calculator, is it? We can do it. Huh? Okay. That would be 3 times 0.25 minus 4 times 0.5 minus 2. That would be 0.75 minus 2 minus 2. So that would be minus 3 1/4, isn't it? Minus 3.125. So it's less than here. So now I'm guessing it's between these two, between 0.5 and 1. And which would you guess it's closer to? I'm guessing maybe closer to 0.5. So let's do 0.7 maybe. So plug that in. You can keep doing this until, I'll call this the method of exhaustion, till you get tired and say, I think it's close to that, okay? And if you get ballpark there, you're going to get credit for it. Let's see what the book said. 0.67. I was guessing 0.7. Not going to be too bad. If you had guessed 0.7, I'll say, yep, that rounds off to 0.7. See how you do that? You don't have to have a graphing calculator. Just look at your values, and the two smallest ones, you know, is in between those two. If it's negative here, more negative there, but positive there, go for these two. And when you pick a value in between those, that gets you that. That's in between these two. And so let's go with, that's what I said, 0.7. Okay? And you do 0.7, and I don't know what that gives you. It's either going to be less or greater. Then keep bracketing, going down until you say, okay, I'm tired of something close to this. Okay? Yeah. No, I pick a number. I picked 0 to start. And then you told me to go to 1. So we went to 1. And that got more negative. And we knew we were looking for a relative minimum. So go further to the right. But that shot me way up to +2. Not a huge amount. So now I go, it's between these two. So pick a number between these two and figure out what the function is. That's closer to the relative minimum than that. So it goes something between 0.5 and 1, but closer to 0.5. I said 0.7. And if you do 0.7, you'll get a number. And then depending, whatever it's between, pick a number between those two. After a while, you'll get tired and say it's close enough to 0.7 or something like that. And that would have been the correct answer.
Negative 3.25.
Where
did that come from?
That's when I plugged in 0.5 here.
Uh-huh.
Okay, Okay, 0.5 squared is 0.25.
Right.
And then plug that in. And then I did, this is 0.75, this is minus 2, that's minus 2. This is minus 4 plus 0.75, it's minus 3.2.
Why are we minusing the two though?
It was, okay. 4 times, negative 4 times a half is negative 2. That's that, well,
Okay,
that one.
okay,
And this
okay.
was a negative 2 always, right here. That stayed through the problem always.
Okay, okay.
So I found that. I could have gone again between, yeah, like I said, I would have gone 0.7 next. See what that gives you. Then it's either probably going to be between 0.7 and 0.5, 0.6. You know, keep doing until you narrow down, and then you get tired and say, okay, it's close enough to that. That's as good as I can do. Okay. Or you can use your graphing calculator. There's a checkpoint there, well worth your effort to do that checkpoint. Okay? And let's see, is it that sad time? Oh, I'm afraid it is. Okay, we'll start next time at average rate of change. And what, I don't know if you'll be surprised or not, you'll find out we've already done this. We just called it something else. But we'll do that next time. All right, yes?
How do you know when to stop? That's what I was going to say.
Okay, well, that's why I said it's the method of exhaustion. When you get tired and say, look, I think it's close enough, you can say. I would have stopped maybe at 0.7. Okay, but to see, after a while, you've not got much change at all. It's something around this, okay? If you have a graphing calculator, it'll give you approximately an answer too, but it'll be a lot more precise than that. Okay, homework exercises. I know you don't want to leave without these. Well, we're almost through. Do either 7 or 9 or both. They have 4 parts each. Do either 11 or 13, okay, or both if you choose. Do any of the odds 15 to 23, any of the odds 25 to 29, and we did some like that, both of that last 2 sets. Then do any of the odds 31 through 37, we did them like that. And then do any of the odds, I gotta see. Y'all wait? Okay. 39 to 45. And then you can do any of the odds 47 to 53. Okay? And we'll stop there and pick up the rest of those. Actually, I think you can do I think you can do 55, any of the odds 55 through 59. Let me see. Yeah, any of the odds 55 through 59. We haven't done them exactly like that, but we've come awfully close. Okay? And then after that, you can, we'll pick up the rest of those next time. All right, good deal, folks. And have a good weekend. Of course, working on math problems and doing your research papers be a great thing to do, wouldn't it? And get those 4 bonus points.
You have my whole weekend.
Okay. All right. Get it to me by Tuesday. That's the last day of January. You'll get your 4 bonus points. Y'all have a good weekend.